force is something that we apply to an object that will cause it or tend it to cause it to change direction. So if it's at rest, it would cause it to move. If it's moving, it would cause it to change direction, right? Yeah. I understand that. Now normally we calculate force. I think Tim said it's pressure, how much pressure we have, and then how much surface area the pressure is pushing against. And that's the way we measure force. So to measure pressure, we basically generate a force. So we cause something to move, and then what we do is we either use that motion to triple switch on a digital pressure sensor, right? You understand that? Or we use it to turn an LVDT or move an LVDT or move a potentiometer or something like that to actually measure the pressure. That makes sense? Or we use a solid state pressure sensor. Some of the things that we use to actually sense the pressure, and I can't find it, but let me bring up my PowerPoint. I'll bring up a PowerPoint, and then on Class Ridge. Load sensors. So load sensors would be pressure and force, right? But one of the things that we use to convert a pressure into a force or into motion is we use what we call a bellows. I don't know what a bellows is. Could be rubber. Most of the time, it depends on pressure. A lot of times, it's in these, it's made out of brass. But we come up here, and basically, it's ridged. And of course, if I was to draw this one, the ones we have are circular. Huh? I don't have the projector. That would help. So an accordion is a bellows. So a bellows, y'all seen an accordion before, right? It's got the bellows in there, and when he stretches it out, it pulls the air in. So it's got a check valve in there, pulls the air in, and then when they push it, the check valve closes. It makes it come out through the whistle that we saw. So this would be a bellows. And bellows can be used to sense different types of pressures, and I'd have to go back and look at these. We have atmospheric pressure. I know it's probably spelled wrong. So what we do is outside the bellows would be exposed to atmospheric pressure, which is what's the pressure? 14.6 psi at sea level. And we use this a lot. So when I come up here, if I get up above 14.6 psi, then what's the bellows going to do? It's going to start expanding, right? And that the expansion would be relative to an atmospheric pressure, which we use this a lot, but we're used to atmospheric pressure, right? You understand that? The only problem with this, of course, is that your gauges would be different, a little different, depending on your what? Huh? Depending on sea level. So if you're above sea level, the pressure gauge would be a little higher because you have less atmospheric pressure. If you're below sea level, it would read a little lower because, and there are some places in the United States that's below sea level, right? Then we have one called absolute pressure. Guys, I'm going to have to look these up sometime again. And of course, I think absolute is relative to 0 psi, so you actually run these in a vacuum. So the outside of the bellows would be inside a vacuum, and then your pressure that you're measuring would come in, and so those would be the most accurate because those would be relative to 0 psi. And then we have another called gauge pressure. I can't remember, and we'll look these up. Make sure I'm telling you right. Another thing that we can easily do with a bellows is we can come in and do a differential pressure. And I'd have to figure that out. So we'll go back and look at it. So a bellows, we have a bellows. We have what we call a Bourdon tube, B-O-R-D-O-N, I think. Is that right? Or Bourdon? Let me look these up. My brain's going dead. And this is probably, all these are probably in the lab that we're going to do on pressure. So right now we're working on proximity sensors. And then the next lab will be on liquid level sensors, which we went over. And I think the third set of labs we're going to do is on temperature sensors. And the last set of labs we'll actually do is on pressure sensors. So this is what I'm looking for. So absolute pressure, gauge pressure is indicated by adding G to the unit of pressure. For example, if pounds per square inch is used, then the pressure unit is pounds per square inch, PSI. When used in SI area applications, dry pressure, liquid field. No, that's not. Differential absolute pressure, the pressure measured above a perfect vacuum. So I got that one right? Differential pressure, this is when we compare two pressures. That's the only thing this one right here talks about that I see. And then talks about diaphragm, which we have. It talks about I'll have to go back and probably read the lab. Anyway. So bellows, are you okay there? Yes or no? The other thing that we use to measure pressure is something called a diaphragm, which works on the basic principle of So this is a diaphragm. So you see there's a kind of like a bellows. Huh? Oh, I can make this full screen. Is it okay?
Yes.
I downloaded this. So this is a diaphragm type. So there's a diaphragm in here. We put pressure on here. It causes the diaphragm to expand, right? Then this comes out, this arm right here. And then we can attach whatever we want to measure out here. Normally it would be a limit. If it's digital, it would just be a limit switch, right? So a lot of times on your pressure sensors, we combine we have a sensing element, which would be sensing the pressure, and then we use another sensor to actually convert it over into something we can use. But we still call it a pressure sensor. Does that make sense? You understand what I'm saying? An extremely popular one is a board-on tube. And y'all played around with board-on tubes even if you didn't know it. So we call them the old party whistles everybody's play around with. It's got the spring in it. And when you put pressure on that thing, what does it do? It unrolls.
Oh, yeah.
When you take the pressure off, what does it do? Spring back. That's a board-on tube. That's basically the same concept. So what we have is we have a tube. Notice it's in a coil. See this? Of course, this is made out of metal. And then when we come in and apply pressure, what does this thing want to do? Well, it wants to straighten out, right? You understand? Okay. You can see this whole unit in here moves. I'm going to do it with my hand. So this whole unit in here moves. And then, of course, what we want to do to sense the pressure, we would attach out here on these levers, right? That makes sense? So this is a board-on tube. Very accurate, very, very... It's used a lot. This look familiar to any of you?
Yeah.
This is a typical pressure switch for a compressor. We have problems, and I'm going to show you a video. So when I do regulation, we have problems. So I've got an error. So it says I need to turn my compressor on. So we turn our compressor on. Well, as soon as I turn it on, it builds up the pressure. Now, if I had it set at 100 PSI, what would my compressor do?
It would kick it to 100 PSI.
And then it would constantly do what? As soon as it got up to 100 PSI, it would turn off. As soon as I did something, it would turn on. So my compressor would sit there and constantly do what? Oscillate. We call that proportional control. So using proportional control, the devices have a tendency to oscillate. So you set a set point, and when it gets to that set point, it cuts it off, and then as soon as then something happens and it slows down, right? You understand? So that would be kind of like your car on a cruise control. You get up to 100, you get up to a certain miles an hour, and it cuts your gas off. As soon as it cuts your gas off, your car slows down, right? You understand? And then what does it do? It cuts on. So your engine would constantly go on. So how do we compensate for that? So if I've got a control like that constantly looks at a certain set point, it's going to be almost impossible to keep it from oscillating. As soon as it hits the set point, it turns it off. As soon as it turns it off, what would happen? It would start dropping down, which would turn it on, off, on, off, on, off. We call that a proportional control. So what do they do on a compressor to prevent it from oscillating? They have a we call it a deadband. So it's deliberately got a deadband built into it. So what it is, it's got a pressure that it goes up to and cuts it off. And then what does it do? Then it waits till it get below pressure and cuts it off. And we operate our air tools. We should operate our air tools below the lower cutoff, right? So if I operate it, so if I've got it comes back on at 70 psi and I operate all my air tools at 60 psi, then we should always have a constant pressure and we should always have a constant flow, right? Does that make sense? Yeah, well, usually more than that. Usually most compressors operate 100 psi to 70 psi. That's pretty standard. So you got a 30 psi margin there. Because even 10, your motor would still be doing what? You know, it'd still be oscillating a lot because it don't take long for that pressure to drop.
What gives it the SCFM?
What's that?
What gives it the SCFM?
The
Operating pressure.
Well, that is not the pressure, that is the flow rate.
Oh.
Yeah. The flow rate determines the displacement of your compressor, how much air it can move. So I can take a little tiny compressor that you used to blow up a tire, and I can put it on a tank, and as long as it didn't have leaks, it could charge up to 150 psi, right? You understand? But it'd have a very, very low flow rate. So what determines the horsepower of your car? But it's basically how much air that motor can get through there in a certain amount of time. So that's why, you know, 12-cylinder engines get more horsepower than 4-cylinder engines because they have a bigger displacement. They can move air through the engine fast. So when you talk about cubic inch, what is cubic inches? What does that tell you? That tells you how many cubic inches of air that motor can move through that engine. So it's not literally the size of the engine. A lot of people take that as the size of the engine, but it's not. When you have a 350 cubic inch engine, it means that sucker can move 350 cubic inches of air through that engine in one revolution. And that's what it means. So on compressors, we use different flow rates. One of them's at sea level and one of them's absolute. I can't remember which one. But that's the flow rate that compressor can move. So if your tank went dry and you started running off your compressor, that's how fast the thing could run. That makes sense? So that's that rating on a compressor. How much air it can move. A good question. So now you know about cubic inches on engines now, right? Now motorcycles we usually use cc now. We don't use cubic inches anymore. Huh? But it's the same thing. It's how much air it can move through that engine. So that's why sometimes just changing your exhaust system out on your bike, you can get more horsepower out of it.
Full-time horsepower.
So I don't know if this is rated on here. Yeah, so this goes off at 100 psi and comes back on at 70 psi, which is real standard for a shop compressor. And then our tools are usually designed for 60 psi. You get people that run them higher, but what you find out is your tools will wear out, the seals will go out on your tools. So I don't know. So it allows us on our compressor to use what we call intermediate duty motors, so the motors don't have to be as good, right? You understand that? Because they're not designed to run 24/7. So a continuous duty motor is a motor that's designed to run 24 hours a day, 7 days a week. So if we look at this little three-phase motor over here, you'll see that it's what we call a continuous duty. But it would cost more than an intermediate duty motor, right? So if I've got a pump on my pool, then it's going to be a continuous duty motor, right? So continuous flow compressors cost, they use turbines and stuff like that. Those are really expensive. But you can see we combine these with other sensors. We still call them pressure sensors, right? You understand? But usually when we get into force or pressure, we have to combine that with another sensor. Except for strain gauges. Strain gauges are pretty neat. I did bring our impregnated copper thing from that. I think I did. Anybody got their meter? You got your meter, you can, I'm not gonna do this up here, y'all can do it back there when I pass it around. So, this is one of those homemade pressure sensors, or force sensors. And what we've done is taken this carbon impregnated foam, which varies its resistance with pressure, and then we encapsulated that in between two metal plates, and then it's taped together with electrical tape. So what you need to do is put your meter on ohms, and then just connect it to the bottom plate and the top plate, and just come up here and press on it. And you'd be surprised what this thing could actually measure. So it would actually change its resistance a little bit, even if I put this thing right here on it. So this is a carbon impregnated foam sensor. You got your meter, you can look at it. If you don't have your meter, which you're supposed to bring to class anyway, right? So if I was going to regulate the speed of a motor, I can't use the deadband, right? You understand? Because if I wanted it to run at 100 RPM and I had a deadband of 100 and, at 70, then the motor would still do what? Oscillate. If I use just a tach generator and set it at 100 RPM, then it's going to oscillate too, because what's going to happen is it's going to go up to 100 RPM, and the tach generator says I'm at 100 RPM, and the motor's got inertia, so what's it going to do? It's going to overshoot, right? And then your tach generator says you're going too fast, and it says slow down, and what's the motor going to do?
Slow down too much.
Yeah, it's going to slow down too much, right? Because the motor, once a motor's got inertia, so when we're dealing with things that's got what we call inertial, we can't use just what we call proportional control. So I'm going to show y'all a video. So one of the main controllers we have for analog sensors, not digital sensors, because digital sensors just look for something either way. It's either there or not there.
Yeah.
And we can compensate for proportional control oscillation by setting in a deadband. We can get by with that with some sensors, but some sensors we can't. So when we get to our pressure sensors and our temperature sensors, if you look at the temperature sensor back there, you'll see it's got two adjustments on it. One of them would be for your upper limit, and one of them would be for your lower limit, right? You understand? So normally on your compressor, your air conditioning, your heating system, it don't oscillate because it's got a what? It's got a deadband built into it. But it's not like this unit right here. So this unit right here uses this guy right here. If the heat's on, it's on. If the air conditioning on, it's on, right? You understand? And then what they do is a proportional control where they always, the way these systems work is they run the heat and they run the air conditioner year round. And then it's got a little vane up there that adds a little cold to the hot or adds a little hot to the cold to maintain a constant temperature. So if you go into these guys, you'll see that these are basically running all the time, unless they turn them on. So is it going around? Y'all looking at it? Play around with it. Pretty neat. So they came up with a method, and it's been around for years, where we do a little calculus. So we do two things in calculus that we don't do in regular math. We do what we call integration and differentiation. So integrators and differentiators, which is, if you take calculus, it's real fun to play around with. But I've got a video on, so we have what we call a PID controller. So proportional controllers have a tendency to oscillate because they're trying to maintain something, and it raises something up and it overshoots, and once it overshoots, it cuts off and it has a tendency to oscillate. Integration looks at error over time. So this guy's real slow and trying to get it up to the point. Then we have what differentiation, it looks at trying to get things, it looks at what's trying to happen in the future. Does that make sense? So we combine these into something called a PID controller. So most of your sensors that control a closed loop system that has inertia, like motors or temperature control and stuff like that, is probably going to be what we call a PID controller. And this guy right here makes it, he uses a little profanity, but it's not too bad. Probably.
In my class.
In my class?
It was, I mean, as you play the sound and stuff, you're making something really annoying. Sort of buzzing sound at different frequencies, at different time intervals. So you can't find it.
And then after this, well. So this guy lets it slip every once in a while, but it looks like called PID controllers tutorial. Oops, let me pause it. Hook up my speaker. So this guy's into quadricopters. And so quadricopters, when you calculate them, you know, they try to maintain a level, but it's got all this stuff going on that you wouldn't believe.
Stands for something. Obviously, the P stands for proportional, the I stands for integral, and the D stands for derivative. So there's everything you need to know about PIDs. Now, of course, I'm joking. It's actually quite a complex thing, but I'm going to try and distill it down now. I'm taking a few liberties to make life a little easier for all of us. And I'm going to give these other names. I'm going to give these, and you'll see why in a moment. I'm going to give proportional, I'll give it the name present, as in right now. Integral, I'm going to give it the name past, as in it's already happened. And derivative, I'm going to give it the name future, as in hasn't happened yet, but it's going to. These are the alternative definitions. Well, this is how things work. And I'm going to explain how that works. Now, let's assume this is a mini quad. There it is. Beautiful, isn't it? Gorgeous. I've taken the propellers off because it's always safer to work on the whiteboard without propellers on. And this mini quad has the ability to tilt and whatever. And so we have inputs which go into it from our flight controller. This is all on, here's our flight controller. It's got all this stuff on it here. All this is in our flight controller. This is the magic that makes things happen. And also in the flight controller, there is another block, which is the sensor, which actually, we'll just put it over there. And the sensor provides the information that goes off to the derivative, the integral, and the proportional. So I can draw some lines around these to show you what I'm talking about. These are actually separate bits of stuff. They're actually software inside the flight controller that handle these particular operations. So what we have here is a feedback loop. This is a feedback loop. Basically, here's our quad. If our quad tilts, this little bit here, the gyro or the accelerometer, picks up the fact it's tilted, feeds the information into these things here, the PID software, which then has some outputs. There's a proportional output, an integral output, and a derivative output. They're all mixed up here and then fed back into the quad to correct it. So it's a feedback mechanism that works a little bit like this. Say you're running yourself a nice hot bath and you turn on the taps. Woohoo, all good. Put your hand in. Whoa, it's too hot. What do? You turn down the hot tap. That's the feedback. So first of all, you sense, oh, it's too hot. That's the sense, that's the spit. And then you say, you work out what to do. If it's too hot, I need to turn down the hot tap. So come out here, and then you put that in, and the response is that you turn down the hot tap. Then it gets too cold through this feedback loop to make sure that the temperature is stable and at the temperature you want. That's really simple when it comes to things like running a bath. But when it comes to flight controllers, it gets a bit more difficult because lots of things are happening very quickly. So let's discuss what proportional is. Proportional is like saying, oh, it's too hot, add cold water. Or it's too hot, turn down the hot water. And the amount, if it's really, really hot, then you might turn the hot water right off and let the cold water cool it down. So the amount of adjustment you make is proportional to the amount that the correction needs to be. So let's say you're flying your quad. I've got a uni-quad here. Let's say you're flying, wrong color, it doesn't contrast well on the board, does it? Let's say you're flying your FPV glasses and it tilts like that. If it tilts a little bit, well, you only need a little bit of correction through the feedback to bring it back to level. If it tilts a lot, you need a whole lot more correction. So the amount of correction is proportional to the amount that it's veered away from the desired attitude. So the more the quad tilts or banks, then the more feedback you'll get through this proportional thing. And it's right now. If the quad is at 45 degrees right now, then the feedback will be 45 degrees worth of feedback. If it's at 90 degrees right now, it'll be 90 degrees worth of feedback. So that controls the amount of change in the motor speeds and everything. That's really simple. You might think, whoa, that is so simple. And another way I like to do it, or to mention or talk about it, is, get rid of these pens for a start. Here's, here you go, see? This is my stopwatch. Now, obviously, as I move this away from if I let it go, it just hangs there, right? It just hangs vertically down because gravity is pulling it down. If I move it away from that perpendicular position, or the vertical position, then gravity tries to pull it back. And the further I pull it out, the more the force of gravity is having an effect. So if I move it out a little bit, then it's only really moving a bit. Up there, I can feel a lot of force trying to pull that back to the vertical position. So the effect of gravity is proportional to the angle at which I move this. And you might think, well, hey, that's really cool, because all you got to do is just have this proportional thing. If the bath's too cold, add hot water. If it's too hot, add cold water. Simple. What could go wrong? Well, I'll show you what could go wrong. If I take this and let it go, whoa, hang on, it's swinging. It doesn't just go back to the vertical and stop. It's going past it. It's overshooting because proportional on its own doesn't work very well when you've got something that's got mass or inertia. Because as this pendulum comes back to the 0 point, the effect of gravity is reduced until, as you say, if I let it go here, gravity's not doing a damn thing. But because when I get to there, gravity stops doing its thing, but this has got a mass and inertia, it continues swinging. So that's why we get this oscillation. Woo, woo, woo. See that? And if you have the proportional, the P on your flight controller turned up too high, your quadcopter will oscillate too because it's yo-yoing past because it's not anticipating the fact it's going to go back to the correct position, and it overshoots. And you get the oscillation. The higher the gain, the more proportional feedback you have, the worse that oscillation. If it's too bad, it'll just flip because it goes way past the point of no return. So the present proportional measures the present position of your quad, or the present error that needs to be corrected. It only works in the present. So that's the problem, because if you take instantaneous snapshots and your pendulum goes from there to there, at that instant, which is the present at that time, it's fine. So it just turns off the corrective signal, and the inertia then takes your pendulum back past that point. So it doesn't take into account the past or the future. It's a very limited feedback mechanism, just using the proportional. That's why we have these other things. We've got the integral, and that basically looks at things that have happened before. And that's important, because one of the problems with our correction method here is that if we have a very slight tilt on our quadcopter, or our FPV glasses in this case, the amount of correction being applied by a proportional feedback is very, very small too. So if it's small enough, you might not get any actual correction occurring at all. What that means is that it can actually just hold a little offset for quite a long time. So it gets all loose around center, because the closer it gets to the right position, the less feedback you're getting from the proportional side of the feedback system. So it means big angle, lots of feedback, little angle, not much feedback. So it gets all wobbly and loose around the center. That's not very good. And if you try and make it tight around the center, you end up with so much gain that it wobbles and crashes. So the integral does something really clever. It looks at what's happened before. It goes back a bit in time because it's keeping a track of where this has been. And if over time it finds that this angle has been sustained, it says, that's not right. We need to correct that. So it then starts producing another corrective feedback force, which will force it to go level. So the integral feedback actually increases over time. So whereas proportional is constant, reliant only on the angle, the integral feedback will over time increase until it's enough force to push your thing back to the right position. So we can't use proportional on its own without getting oscillations. We can't use integral on its own because it's too slow. It would take forever for your quadcopter to right if it got kicked up by a gust of wind. It would be really, really horrible and sloppy. So proportional deals with what's happening right now. Integral looks at the past and takes into account the fact that something has been, hasn't been corrected sufficiently, and it will add the extra correction. Really important. Then we've got derivative, and this is a really freaky one because this is looking into the future. This is time travel shit. What happens with derivative is it doesn't look at the present or the past. It looks towards the future. It tries to work out what's going to happen next. So if your quadcopter is rapidly rotating, it can see, hey, it's rotating, so in X units of time, it's going to be here in the future. So what it can do is then apply correction. Because, for example, if you've got this big angle here and suddenly it's been corrected, and the derivative software works out that if we wait too long, it's going to overshoot there, derivative can apply correction to stop it at just the right time by anticipating the movement of the quadcopter. So derivative will damp out those, if you do a sudden change of pitch or roll, and don't have enough D, enough derivative, it will wobble like that. But if you wind the D up, it will damp it and it will stop exactly because it's anticipating, thinking, this is going to go too far. Our pendulum, for example, is going to swing past the 0 point and we're going to have an oscillation. So what the derivative does is it says, I know the pendulum's going to be here, and when it gets there, I'm going to apply corrective force. So in that case, with the right PID setup, your pendulum just goes pop and stops. It doesn't rock backwards and forwards. If you had integral, your pendulum would take forever to get back to the right point because it looks over a long period of time and averages all the numbers. So it's a very slow correction. If you had proportional, then you get this oscillation. And if you have proportional, integral, and derivative all mixed together in the right proportions, then the pendulum stops exactly where it's supposed to be. And the same happens with your multi-rotor. When you've got your PIDs tuned, it responds immediately to your stick inputs. And when you stop putting a command, it stops exactly. And it feels locked in and tight and directly connected to the sticks. That's what PID do in simple terms. What I'll be doing in a future video is showing you how to make sense of this in terms of programming your flight controller, what to look for. But what I've tried to do here is simplify this whole PID thing and basically explain how it works in terms of the inputs that are being put back in here, this feedback loop, how each one of these does something different to make for a feedback loop that doesn't oscillate. It is very quick to respond. So there you go. I'll probably confuse the snot out of you. Never mind, that's what I'm here for. Got questions, got comments? Let me know about this PID.